So, and this is about collapse models or models of spontaneous wave function, where a collapse of the wave function, and which basically, if you just a little bit of history. So the discussion started in the late 70s. The discussion started, and the main actors were Girardi, Pearl, Dioschi, Gizen. At those times, probably I'm forgetting someone, so it's not a rigorous history. But the turning point was in 1986 with the GRW, which the GRW model. By the name of the three authors who co-authored the paper in that year. Then several models came out, and probably the next relevant step is 1990 with CSL. CSL stands for continuous spontaneous localization. And then we come, so again, much went on till we come to this century with experiments. So it took quite a bit of time, as usual, of course, for this model to pick up, to become really something interesting for a physical community, to the point that also experimentalists are now, so no dedicated experiment, not really dedicated experiment has been done so far, but experimentalists have started talking about it, and about the interest in testing possible deviations from standard quantum theory. Did I make a mistake in canceling it? Okay. And so the moral, what is the moral, the main idea of behind collapse model? So the idea is the following one, the idea that you want to modify the Schrödinger equation by introducing of suitable nonlinear and stochastic terms which mimic the collapse of the wave function. So that's the moral. Why? I guess you know, or you have from the previous lectures or from your own interest, because of the measurement problem. So you well know that you can have you well know that you can create the superposition of microscopic states, and in particular the superposition of the microscopic systems located into different positions in space. So you can have many types of superpositions, but the one that are more striking for us, for our understanding of nature, is that you can create superposition in space, here plus there. And this has been seen repeatedly in experiments, first with electrons, then with neutrons, with small atoms, and the famous 1999 experiment by the group of Anton Zeilinger in Vienna, which is perhaps one of the milestones, or without perhaps. And now with even larger molecules, you can create a superposition of the delocalized center of mass state, and you can make it interfere, and you can see the interference fringes. So it's something really astonishing. But the theory tells that even an object like, I don't know, I try to make a chair, no, with the man sitting. The theory tells you that since it's linear at all scales, there is no reason, I don't know, experimental evidence of a breakdown of a superposition principle so far. And actually, since people would think that quantum mechanics applies to all physical systems, to the point that people are using quantum mechanics, and more specifically quantum field theory, as a necessary ingredient for describing the evolution of the universe. So they describe the small things, they describe the very large things, so quantum theory should describe also middle things, like us, like tables and chairs. And since it's a linear theory, in principle, it should have a superposition also of a chair here and here. This is not part of our experience, this is not part of our understanding of nature. Macroscopic objects are always localized in state, and this is the problem. This is the problem, and you've heard in the past days, I guess, that there have been several solutions to the problem. I think you've been exposed to Boomi mechanics, and collapse models are another possible solution. And so the motivation for, and the solution is provided by modifying the Schrödinger equation, by modifying the superposition principle in such a way that in this new dynamics, this is still allowed, but this is not allowed. And we will see how GRW, basically for the first time in a successful way, was able to construct a consistent dynamics. Of course, it's easy to make something ad hoc. Just let this happen and forbid this from happening. But you want to have a consistent dynamics which works for every physical situation, not just for these specific situations, which in principle can describe everything we know of nature. And that's the big challenge that collapse models were able in fulfill. Okay, here, but in this part of the lectures, I want to stress this character of the dynamics because it will give you an idea of how, in a sense, difficult the problem is. So if you want to modify the Schrödinger equation by forbidding the superposition of superposition of macroscopic states, this dynamics has to be linear. It has to kill superposition. So it must be nonlinear, sorry. It must be nonlinear. And then the question rises, can we modify the Schrödinger equation, the unitary dynamics, by adding nonlinear terms, so make it explicitly nonlinear? This question was resolved within collapse models, but was asked by several people also outside collapse models and the motivations for collapse models. It was particularly asked by WEINBERG, in 1989, if I remember correctly. He posed the following problem. So the superposition principle is the fundamental and most striking feature of quantum mechanics and quantum field theory and of any quantum theory so far. Isn't it the case that this is just a special case of a more general underlying non-linear dynamics? And this is actually something, if you think about it, is something very natural to think about. That linearity is just something like the first order Taylor expansion of a deeper level theory. So think of gravity, general relativity is linear, but the weak field limit is Newtonian gravity, which is linear. You can superimpose Newtonian potentials. So the same, perhaps it's true for quantum mechanics. Quantum mechanics is linear because it's just a low energy limit of a deeper level nonlinear. And that's the question that he asked. And he proposed a model for a nonlinear modification of the unitary evolution of quantum field theory, more specifically, and also an experimental way of testing that. But then, soon after, Gizen and Polchinski independently proved him wrong. That you can't unless you're willing to do superluminal signaling. Superluminal signaling. Okay, and this is what I will, basically now I will start really with. I will give you the argument why, if you try to modify the Schrodinger equation in a nonlinear way, you almost unavoidably do something bad, something that you wouldn't like to have, which is faster than light signaling, instantaneous communication at arbitrary distances. There is only a way out to that, and the way out is precisely that of collapse. And so in this sense, collapse models are the only, or belong, if you wish, to the only class of possible modifications of the Schrodinger equation in nonlinear. Of course, there is always the path open to a radically new theory, out of which quantum mechanics emerges as an approximation. But if you want to stick with the quantum formalism of wave function, of states represented by wave function in Hilbert spaces, then, and in particular with the possibility of having entangled states, then you always, basically always do superluminal signaling, unless you go the collapse model way. Okay, how do you see this? So we are in the quantum formalism, we have an entangled density matrix, and we have a setup that you are familiar with. Entangled states, part of the system moves to the left towards Alice, part of the system moves towards right to Bob. Think of two entangled photons or whatever you wish. We can stay rather general. And Alice here decides has the possibility to measure two observable quantities among the many. So after the measurement, what happens? So how does the state for Bob change after the measurement? So before, there was an entangled state, which is this state that evolves the way it evolves. But then after the measurement of Alice, you have a reduced state for Bob, which is the following one, that I also hope you are familiar with from quantum theory. So suppose that the observable k is 1 or 2. Yes? Little bigger. Yes, I will. Well, let me rewrite it here. Is it sufficient this way? So what happens here? So so K is equal to 1 or 2, so it's any of the two observables. That is, you have the spectral decomposition of the self-adjoint operator with eigenvalues and eigenprojectors. So it's just a spectral decomposition. And this is what quantum mechanics, or if you wish, I mean, or you can take also an alternative theory, but any alternative theory has to match with quantum mechanics in this regard, because people did this type of experiments many, many times and successfully reproduce quantum predictions. So this formula must be true in some sense. That when you have an entangled system, at the end of the measurement process done by Alice, Bob has a statistical mixture which is defined in the following way. So you take the state, you project it with respect to all possible eigenprojectors of the measured quantity. So this is the collapse, basically, the collapse state. You normalize it. So you collapse the state, you normalize the state, and then you have to make the incoherent mixture with, when you sum over all possibilities with the correct quantum probabilities, which is the Born rule. And actually, I'm making here very simple steps just to point out the important concept, if not already familiar with it. And then the important property of quantum theory is that the probability, this weight, which is the probability of the mixture, is the probability for Alice to have found the eigenvalue of nk in a measurement, which is exactly given by this expression. So the normalization factor for the collapse state also is equal to the probability. So the two cancel, and then you simply have sum over n This is the final output, the final density. Matrix for Bob, which also is simply the partial trace over A of rho A. So simple things, I hope. But I want to stress one point that, and soon we understand why I stressed that. That mathematically speaking, the effect of Alice measurement on the state is to modify it in this way. This is a linear operation. Okay, so linearity is good, nonlinearity is almost always bad. So Alice measurement, or better, Bob perceives Alice measurement, mathematically speaking, as a linear operation performed on the state. Why is it a linear operation? It is a linear operation because I was able to make this cancellation over here. Without this cancellation, this transformation would not be linear. And why could I make this cancellation? Because the probabilities of the measurements are given by the Born rule, which is the normalization factor. So the Born rule is an axiom in quantum mechanics. But then from here and from the continuation of the argument, so it's basically I'm repeating the no super signaling theorem. The Born rule has a specific role. It is the unique probability rule within quantum theory that forbids you from doing superluminous signals. So it is, you might think that when you see the axioms of quantum theory that it is just a probability rule, well, who cares? So nature has chosen this one and not another one. But actually it's a unique one that in spite of the nonlinear character of the collapse, of the non-local, character. So there is something non-local going on here, which is expressed by Bell's theorem and Bell's inequality. So the collapse is non-local. But unluckily, the Born rule does not allow us to use non-locality to study superluminance. And the Born rule is the only probability rule that does. Okay, now, what is now the point? The first important point, which is the superluminous signaling theory. Now, suppose Bob makes a measurement. After, in some frame, here we are not so much interested in relativity. After. So in some frame, Bob decides to make a measurement actually before or after Alice makes. So if the measurement is done before, OB is just any observable that Bob can use. So this is simply, according to quantum mechanics, it's just this. It's the trace of the operator, the expectation value, the trace with respect to the state. But if we do it after, so if Bob decides to measure this quantity, not before the measurement, but after the measurement, then there is already reduced density matrix for Bob, so Bob can simply take the trace with respect to his Hilbert space of his observable with respect to his state. And that becomes, so just to, again, warm up a little bit. Here I just rewrote the definition of the reduced density matrix rho B. K, sorry, this is, I should have put in a K, sorry, here, because Alice can decide to measure two different things. And then you know that now how to proceed now. You can bring the sum out because of linearity. Then you can bring this one here because of the properties of the partial trace. You can bring then it here because of commutativity of the two operators. And so basically, since these are projection operators, the square makes 1. No? Tell me if it's too fast, but I think it's something that you are familiar with. Then you can bring the sum back in, make the sum, and this sum becomes 1. And so this is equal to the trace of 1A cross OB rho A B, which is the trace over B. Well, I will leave it like this because it's the same formula as before. Okay, so, and you see the moral here. The moral here is that whether Bob does the measurement before Alice or after Alice, nothing changes in the statistics. So something changes because in between Alice has made a measurement, so the ensemble of states is different from before. Before you had an entangled state, and you could do Bell type of experiments and check locality. After the measurement, you have to separate direct product states. And if you do Bell type of experiments afterwards, you lose this. You have lost entanglement, you have lost also locality. Nevertheless, for Bob, without communicating with Alice, for Bob, nothing changes. Measurements, statistics of measurement done before Alice's measurement with the entangled states are the same as the statistics done after the measurement with the collapsed state. And that's the no faster than light theorem. So quantum mechanics does not allow for superluminal signaling. Incidentally, those of you that know about quantum field theory and have taken quantum field theory courses, this is precisely the meaning of the microcausality condition. When you hear the microcausality condition that operators at space-like hypersurfaces should commute in order to guarantee locality, and they call this property microcausality. So phi of x for a Klein-Gordon field, phi of y is 0 for every x minus y squared less than 0 microcausality. The microcausality condition that you find in books. It's why is this a locality condition? Precisely for what I told you before. Call this one phi of x. So it's a function. This is the measurement done by Bob. And it's so in a quantum field theoretical language, this operator is function also only of fields around Bob. This one, call it phi of y. This pertains to Alice, so these operators are functions of the fields around Alice. And if we are in a space-like separated setup, which is implicit in the argument, then x and y are space-like, then they commute, and then I could make this is the relevant step. I could make that when I bring this here, which I can always do because the trace is cyclic, I can do also this thing. This is the important thing, the important step, that I can commute the two in order to bring this here and cancel that. So the microcausality condition of quantum field theory is a no superluminal signaling condition, which is a weaker requirement than locality as given by Bell. The locality given by Bell is another condition on the statistics of outcome that they should be independent. And this locality condition is violated. It is violated in quantum mechanics. It is violated in quantum field theory. It is basically violated in any quantum field. So just that you are aware that when field theorists and particle physicists talk about locality of physics, they mean the impossibility of superluminal communication. But there is a deeper level of locality, which is in some sense equally important, which is violated by any one. Okay, and again, at the end of the day, everything was possible because of this commutativity condition, but also because the collapse acts effectively as a linear operation on the density matrix. So the collapse is nonlinear on the wave function. The collapse by definition is nonlinear on the wave function because it collapses, it kills superpositions. But it is effectively linear on the density. And this is the other important ingredient. Why we do not have this possibility of superluminal communication. Okay, but so this is yes. Here, I mean that when Alice makes the measurement, how does the state for Bob change? It changes in a linear way. This is a linear operation. I mean simply this, that this is a linear operation on the density. It's a partial trace. The partial trace is a linear operation. I mean the state evolves non-linearly, the wave function. But the collapse, but the statistical operator, let's put it this way. So the wave function evolves non-linearly and randomly. So one initial state, after the collapse, goes in different possibilities with different probabilities, and these possibilities are non-linearly connected to the initial state. But when you add these non-linear possible outcomes to make the density matrix, stochasticity and collapse, combine in such a way that the global effect is zero. So it's a very, so when people talk about locality and non-locality, they give it for granted. The word is relativistic, and so you should have it. But actually, it's not the case. Quantum theory is a theory that, because of entanglement and non-locality, is the theory that just is for a tiny subtle reason is easy, can cope with relativity. But from the way it's defined, it would be a completely non-local theory. And in some sense, it is a completely non-local theory because there is Bell's non-locality. So these things are not granted. There is a kind of magic why they work, and no one really understands why, because it's not natural. Naturally, quantum theory is a non-local theory. It's natural that you have, at least as far as we understand things now. In the future, perhaps with the deeper understanding, things will become natural again. But as we understand things now, it's just a miracle that you have no superluminous signal, because you have all these funny things that have to match. They do, but there is no reason why they should. They just do by ad hoc initial assumptions. Okay, but let's go on with the game. Why? I already used everything. Let's go on with the game. So we were here. So Alice makes a measurement, and then Bob cannot understand the difference between the measurement of Alice. We can understand whether Alice made or did not make the measurement because the statistics remain the same. But now, suppose that, so this is, so Alice makes the measurement, then the state of Bob collapses, and then Bob waits a little bit before making the measurement. And then after some time, he makes the measurement. And now, let's make the, so far we analyzed only the effect of the collapse. The collapse is messy, whatever it is. I just use the standard von Neumann and Born rule. But now let's forget about the collapse. Now let's consider the evolution. And now we come to the argument of Weinberg, which was disproved by Gizen and Kuczynski. So we let the system evolve, and we assume that the evolution is nonlinear. Then what happens? Cancel. So let's call this T0. So this is T0, and then at some later time T, Bob makes the measurement. T0 is the time when Alice made the measurement and collapsed on the other side. So at time T0, so the density matrix for Bob, as I wrote before, is the partial trace over A of rho AB. But actually, it can be written as sum over I, P. I should write bigger, sorry. the density matrix is the same. But it represents two different ensembles depending on whether Alice measures O1 or O2. So these are two different observables that Alice measured. They have a different spectral composition. So the wave function collapses in a different way. So you have different statistical ensembles, but they combine in such a way that there is the same density matrix. Different ensembles that give the same density matrix. No much surprise, the relation between ensembles and density matrices is not 1-to-1, but many to 1. Okay, now, we have the time evolution, the nonlinear time evolution. And so the two ensembles go into yes, still bigger, no. Tell me again, sorry. Yeah. No, not necessary. So you mean O1 and O2 for Alice, they don't have to commute. Then if they commute, yes, then you cannot play the game because they have a common set of eigenstates. And the thing, so if they commute, they have a common set of, so these are the eigenstates, no, of the operator. They have a common set of eigenstates, and then technically the situation becomes a little bit tricky because they could be degenerate. They could have a degenerate spectrum, and then what does it then? They could commute, but the eigenspaces could be different. Could be not necessarily the same. So when you create the ensemble, still, if they commute, they could make different statistical mixtures. I don't know if you're following me. For Alice, no, Alice, the game here is that Alice makes a choice. She measures one, but she chooses which one. And in general, so that if that was the question, yeah, sorry, then I didn't understand. So the game is that she measures one and only one, but she can choose which one, and Bob doesn't know. And the game is that Bob doesn't see anything of what Alice does. Yes. Yes. Say it again, sorry. The collapse is nonlinear by definition. Yes. Yeah, now we assume. We're assuming. No. It's just it's the game of it's the reply of Gizen to the idea of Weinberg. So let's assume that the fundamental Weinberg said, let's assume that the fundamental dynamics is nonlinear. I would not say since then. The collapse is nonlinear, period. I know the story. Now, what about the evolution? So in standard quantum mechanics, the collapse is nonlinear because it's the definition of collapse. So it's not, collapse is not linear because I decided to, because that's what collapse does. It kills superpositions. So the collapse in any form, and in particular in standard quantum theory, it's a nonlinear process. Period. Now, what about the evolution? In standard quantum mechanics, the evolution, so is given by the Schrödinger equation, and it is a linear. So the collapse is nonlinear, the evolution is linear. Now I'm making the game. Let us assume that also the evolution is linear. So we are making a new theory. So it's not standard quantum theory, it's another theory based on vectors, on Hilbert spaces, but it's a nonlinear theory. So if the evolution is nonlinear for the wave function, then any state evolves the way it evolves. Phi I at time 0 in both cases goes to phi I at time t. But the two mixtures, the two statistical ensembles that you have, will not be equivalent anymore. So here, at time 0, they were equivalent. Equivalent means that they give rise to the same. So you are mixing different states with different probabilities, because these are the eigenstates of the operator O1, are related to the eigenstates of the operator O1. These are related to the states of operator O2, so they are different. And the probabilities of getting the outcomes are different in the two cases. So different states, different probabilities, which, however, combine in such a way to have the same density. They just combine. It's just the way it comes out. We proved it before, that rho B carries an index K because it depends on the way, on which choice Alice made. But then at the end of the calculation, it was trace over A of rho AB. No reference to K anymore. It's the same in the two cases. That's interesting. So the two ensembles are equivalent. Then they evolve in time, and if the evolution is unitary, then you can prove that they remain equivalent forever. But if the linear and unitary, but if the evolution is nonlinear, and so it cannot be unitary because it's nonlinear. If the evolution is nonlinear, then you lose this property, and in general, these are non-equivalent. So this leads to rho B1 of t. This is a rho B2 of t, and they are different from each other. Yes? No, this is, no, wait, don't think in terms of rho. It's a nonlinear evolution for the wave function. They go with, yes, there is a nonlinear evolution. Yeah, it's the same nonlinear evolution. No, they're not equivalent. Suppose, very simply, that this is the nonlinear evolution. You can have a non-trivial nonlinear evolution where any of these states goes to a given phi. And any of these, which are different, go to a different phi. A very silly nonlinear, it's a very silly nonlinear evolution. All of them go to the same point, all of them go to the same point. So this statistical mixture becomes a pure state, and this statistical mixture becomes also a pure state, but two different pure states. A very silly example of a nonlinear evolution. When you have a nonlinear evolution, you can do anything. Linearity is a very special property. So that's also what Weinberg does. Linearity is a very special property. With non-linearity, you can do whatever you want. So two initially equivalent rho typically go to two different. Was the example clear? Was my example clear? Okay. No, it is just a silly example of a nonlinear evolution. Suppose that I define the evolution. So psi 0 goes in n psi, goes in nt of psi. So this is the evolution. N stands for nonlinear. It's an evolution. N is an operator defined on the Hilbert space. And then suppose in particular that phi I1 goes to phi, given phi 1 for every I, and phi I2 goes to another phi 2 different for every I. This is a trivial example of a nonlinear evolution. It's a possibility. So all these states go to the same state, and all these other states go to the same but different state. Then this mixture becomes a pure state, right? And also this mixture becomes a pure state, but on different states. So they are not equivalent anymore. Ah, sorry. They can, these two? Yes, they can. But in general, for any physically not idiotic evolution, it would not be the case. Now we see that there is only basically, again, there is only one possible nonlinear way, we will see that. There is only one possible way of putting nonlinearity and preserves the equivalence. So there is a way. And that's the end of the argument. My point is that in most cases, whenever you will guess a nonlinear evolution, you will come up to a problem. That's my guess. So the vast majority, if not almost, probably if we can have a space of nonlinear dynamics with a measure, I would say that all of them, except for a subset of measure 0 of nonlinear evolution, lead to this problem. And actually, WEINBERG, who notoriously is a smart guy, he picked one and he was wrong. That's where, because most of them are wrong. So if you allow, what is the moral of the argument here? So remember, Alice made a measurement. Oh, there was an entangled state. Alice made a measurement. Then so this part has to be true because this has been repeatedly measured in the experiment. So whichever theory you have in mind, with some degree of accuracy, it has to do this. Perhaps you have a different formula, but it must end up to something like this because this has been repeatedly measured in the experiment. So after the measurement of Alice, Bob has two different ensembles because there are two different options for Alice, but they are both equivalent because they sum up to the same density. Now we let system evolve. And suppose that nature is not given by quantum, the description of nature is not given by quantum theory, but it's given by a nonlinear evolution. Quantum theory is just a weak field or whatever. Nonlinear evolution. Then you end up to this situation, and in the vast majority of cases, you lose the equivalence of this. So if the two ensembles are described by different rows, by definition of being different, it means that there is at least one observable which gives different outcomes according to this or this case. So exists OB such that the trace over B of OB rho B1 T is different from the trace over B of OB rho B2 of T. Otherwise, if there is no such observable exists, then you can prove that the two rows have to be the same. But our game is that they are not the same. Which means if this is the case, you can do faster than light signaling. So again, also in this case, we have nonlinearity. So there are two parts here in the argument. The first part that I showed you was the no signaling theorem in standard quantum mechanics. In standard quantum mechanics, the evolution is linear, no problem, but the focus is on the collapse of the wave function. The collapse is nonlinear, and actually, according to Bell, is also non-local. But because of the special way the wave function collapses, which means this part here, and because of the fact that the probability rule is given by the Born rule and not by some other rule, nonlinearity and random and uncertainty of outcomes combine in such a way that the final evolution is linear, and then Bob, and because of this, as we have shown here, no, it was cancelled, you can't do superluminal signaling with the collapse of the wave function. But then but then the story goes on. Okay, we cannot do it with the collapse of the wave function. But what happens if the dynamics, instead of being linear, is let me just finish then. What happens if the dynamics is non-linear instead of being linear? Then the same game runs. If the dynamics is non-linear, basically almost always, except for a few cases, you have superluminal signal. Does it mean that you cannot have a nonlinear evolution? No. I'll answer after the question. If the two ensembles are inequivalent, the definition of being inequivalent is that the two density matrices are different. If two density matrices are different, then there is at least one observable which gives different statistics, because otherwise they would be the same. Now, what happens? How does the game go now? That Alice is far away on Jupiter and periodically makes measurements, either of O1 and O2. Then Bob does his measurements with this one. And if he gets these statistics, he knows that Alice measured O1. And if he finds these statistics, he knows that she measured O2. And that's the basics of information. And in this case, of superluminal communication. No. It would look like that, because collapse models are a nonlinear evolution. So no, so the conclusion, now I come to that. So the conclusion is not that. The conclusion is not that the Born rule prevents superluminal signaling provided that the evolution is linear. The Born rule prevents the superluminal signaling provided that the nonlinear evolution is such that this doesn't happen. So nonlinear evolutions should not allow for this. Does it mean that they don't exist and the only linear evolution exists? No, I will come to that. So the point so far is that if you want to have a nonlinear evolution, then this, and you ask for no faster than light signaling, then this cannot happen. So it must be this thing. So our nonlinear evolution must preserve the equivalence among statistical ensembles, yes?
You are assuming that, this whatever nonlinear evolution, that is at the fundamental level. This is not something like we have an open quantum system and...
No, I'm talking at the fundamental level for the wave function. Yes. Yeah, the game is a fundamental level. For whatever reason. Then it could be given by some field, whatever, but the assumption is that a physical system is described by a wave function, and that the wave function evolves nonlinear. whether you need to take the entire universe to have an isolated system to do the game, that's a practical thing to say. Okay, so now we make the restriction. We consider only nonlinear evolutions which preserve the equivalence among ensembles, which means that rho 1 at time t and rho 2 at time t are the same, and I simply call them rho b at time. Then what does this imply? That the nonlinear evolution, however ugly it is, it defines a map So if this is the case, that you have your ensembles which evolve non-linearly in a crazy way, whatever it is, but such that at any time you preserve the equivalence, then the density matrices are always the same. Which means that from the nonlinear dynamics of the wave function, you can again, like in standard theory, you can build, you can define, you don't have it at the beginning, now you have it, a map on the density matrix. This is a map that maps in and map means that you have to map in an ambiguous way. Rho B is unambiguously mapped in rho B of T. It's a map. Okay, now we have it. Good. We have something more. Yeah, but you know that the point of measure 0 exists. It is of measure 0, but it exists. Okay, so and I will and collapse models is one of them. They are of measure 0. That's why they are special. No problem. I will come to that. Yes. Yeah, I will come to that now when the argument is finished. Yes. So at the moment we have just that will be the end of the story, basically. So it's clear that now we have a map of one row. Before we didn't have a map on row, we had a well-defined map on the vectors. Now, under this assumption, we also have a map on the statistical operators. This map is linear by construction. So the evolution for the wave function is non-linear, and we don't know what it is. We only know that it is such that it preserves the equivalence among density. Then we define a map on rho, we can define, and this map, by construction automatically, is linear. And linear, in some sense, linearity is even trivial. In some sense. So take rho equal to lambda rho 1, lambda 1, rho 1, plus lambda 2, rho 2, with rho equals sum over I, pi phi I, and rho k is equal to sum over I, pi k, phi I k, phi I k, k equals 1, 2. Just a decomposition. Then, rho of t, what is it equal to? Sum over I, pi phi I of t, phi I. Yep. Bigger. Bigger. Okay, so so we take a lambda, which is a convex combination of, rho, which is a convex combination of rho 1 and rho 2, and then you have two decompositions, whatever they are. You have for rho, for 1, a decomposition for rho and for rho 1 and for rho 2. So this is a time zero, if you wish. So what happens to rho of t? So this is equal to sum over I, phi I of t, phi I of t. So we just take, how do we find the time evolution? Just take any decomposition of rho, make it evolve the way it evolves, equivalence is preserved anyhow. But this is also equal, so this is a possible decomposition with the time evolution, to lambda 1 sum over I, pi 1, phi I 1 of t, phi I 1 of t plus lambda 2 sum over I, pi 2, phi I 2 of t, phi I 2 of t. Because this is another, so take it to time 0, this is another possible decomposition of rho, no? Rho is lambda 1, rho 1 plus lambda 2, rho 2 with rho 1 and rho 2 given like this. So if you plug this in there, you have still another possible decomposition. It's just the same story. But this is rho 1 of t, and this is rho 2 of t. And you see that rho, no, you don't see because there is this one, probably. Rho of t is equal to lambda 1, rho 1 of t plus lambda 2, rho 2 of t. So it's a trivial thing linear. It comes out basically for free. So it's the same story as with the collapse. The collapse is nonlinear at the level of the wave function. But at the level of the density matrix, it is linear, and it is this property that allows for no superluminal signal. Now, with the dynamics, it has the same story. The dynamics can be nonlinear. But then, in order for not having superluminal signaling, is that it has to preserve, so the real motivation, the real request, and it has to preserve the equivalence among statistical ensembles. If it preserves the equivalence among statistical ensembles, you can define a map on rho, and this map turns out to be a linear. But you can go also, so basically you can shorten the argument by saying that nonlinear evolution are admissible only if they lead to a linear evolution for the density. But from the argument of the collapse, you might well understand that if you have a nonlinear deterministic evolution, this condition is never met. Just, I mean, that could be an exercise that we can come back in the next hour. Given a nonlinear deterministic evolution for the state vector, prove that you cannot satisfy this condition, unless you're really unlucky. In general, so take a nonlinear deterministic evolution, you will immediately find an example that violates this condition over here. If you cannot figure out the example, we come back the next hour. How do you do? Then, can you still play with nonlinear evolution? Yes, using the same trick that we used here. You can have a nonlinear evolution. I'm not saying this one, another one, for example. You can have a nonlinear evolution only if you combine it with the stochasticity in such a way that the two give rise to a linear evolution for rho. The collapse is one example. Collapse is one example. Here we have shown in a simple way, but the importance is the concept, it's not so much the mathematics, that if you have another nonlinear evolution, If deterministic, then it doesn't work. It will lead to superluminous signal. You can save your evolution only if it is stochastic. But then you also well understand that stochasticity and nonlinearity, they have to balance each other in order to fulfill this condition over here. It's not that if you take any nonlinearity, any stochasticity, put them together, you find the result. No, you are asking something really strong here, that the equivalence among statistical ensembles be preserved at any time, which means at any time, stochasticity and nonlinearity play in such a way that the equivalence, that the ensembles, in spite of being different, they are still equivalent in the sense that they give rise to the same density. Say it again. Well, at the end of the day, I think yes, but the full mathematical proof we're still working on. It's not clear. I'm thinking if you can have... No, you don't know. It's, I think, so you should specify better the statement. I'm not sure. No, I'm thinking about the mathematical structure. So in general, yes. But I don't know if it's a mathematical statement or just what we know so far. So that I'm not fully sure. And that's why, and so that, and so that we come to the beginning of my claim. We come that there is, so if stochasticity and nonlinearity, so nonlinearity can exist in nonlinearity, but it must be combined with stochasticity. And it must be combined in a very delicate way, to the point that there are moral arguments. The mathematical proof is, the rigorous mathematical proof is still missing, but moral is there, for instance. That there is a unique class. I finished the statement. There is a unique class, the unique structure that does the job. And collapse models belong to that structure. So that's the end of the statement. Which trace? The trace is always one, no? The trace is always is a density matrix. The trace is always one. The trace of rho b is one. Yes, the density matrix. Yeah, but they're not the same. Of course, you can have two matrices with the same trace. 1, 0, 0, 1, and 2, 0, 0, minus 1, they have the same trace, but they are different. No, they don't have the same trace. Now they do. I have problems in arithmetic. So the trace is a constraint, is a property, but a matrix has a much larger information. So all density matrices have trace one, but they in general, they describe different states. So the fact that, so the trace was always one here, the trace, but that's not important. Yes? The wave functions. The game here is that the fundamental object, as it is actually in quantum theory, is the wave function, and the density matrix is a derived object which you use for practical very useful purposes. But the fundamental object is the wave function. And then when I took the evolution on nonlinear evolution for the wave function, the evolution for the density matrix at the end turns out always to be linear. But why it has to be linear? It has to be linear for the ignorance propagates linearly theorem, so to say. That what is the true meaning of the density matrix? So let's see it here, just an example. Let's see it here. This is, rho represents an ensemble of pure states, so an ensemble of pure states weighted with some probability. What does it really mean? That this is classical ignorance. So the system, given one system, it is described by one of these states, and only one. And I don't know which one, and so I put a probability. So this is my ignorance about which state. Now, how does it evolve? This has to basically evolve linearly. The ensemble has to evolve linearly, because so the state can evolve non-linearly. But P remains P, it's my ignorance. My ignorance remains the same, whichever way the states evolve. If I know that with probability 1/2 is this state, then with probability 1/2 it will be the evolved of it. So this evolves non-linearly, but then you combine everything linearly. So it's, in a sense, it's trivial. The evolution for rho is always linear. Precisely, so mathematically there is no reason, it's a special assumption, but physically it has to be like that because of the physical meaning of rho. It contains our classical ignorance, subjective ignorance. Okay, so if there are no further questions about this point, now I will move to introducing collapse models. So I hope you just got the general moral that if it is, so now more and more people, and you've seen again, I mean, WEINBERG recently, WEINBERG was one of the defendants of quantum theory. He proposed this idea in 1989, not to disprove quantum mechanics, but to disprove alternatives. And a week ago or so, it came out with a statement that most likely quantum theory has to be superseded by another theory. It's not the end of the story. So now more and more people think that quantum mechanics is not necessarily, of course it's conceptually, it doesn't have to be the right theory. History proves that theory never definite. But now there are theoretical arguments, and there is no experimental evidence of violation of quantum theory. But now there are theoretical arguments to believe that quantum theory is really not the end. But then you face with this type of problems, that if you want to modify quantum theory, it's very delicate. Typically, you do something badly wrong. And so I hope in this way you can, even if collapse models at the end of the day will turn out to be wrong, I hope you can appreciate the value of them and the value of the work of Girardi, Rimini, and Weber of finding a consistent way of modifying quantum mechanics, which after 30 or many years, still cannot count, after many years, it's still there on the market. It could be a viable option. Okay, and so we start with now collapse models. And more specifically with the GRW model. So just a little bit of advertisement first. If you want to learn more, you can have these two. Reviews. The second one has been done together with TP and Henrik, incidentally, and it's a little bit more modern with an update. It was 10 years after the first one. So here you can learn everything you need to know so far about collapse models. Okay, so the GRW model. So I will introduce the GRW model, not only because it's the first one that was that appeared in the literature, but also because it's the easiest one to introduce to understand what the game is. And it goes as follows. So it's a quantum theory. So the state is described, well, also by the wave function belonging to the Hilbert space, and there is no other extra ingredient like particles and Bower mechanics. Here there is just a wave. And of course, if you want to talk about the ontology, the story becomes long. And then there is the dynamics. So how the state evolves in time. And now we'll make the story long, and then I will tell you you can write it even more shortly. So this is in general, psi is a multi-particle wave function in general, not just for one particle. So the rule of the game is that the dynamics is a piecewise dynamic. And in particular, it assumes that every particle of a physical system, in any situation, not just in measurements, anywhere, in the universe, anywhere, independently from the other particles, experiences at random times spontaneous collapses, spontaneous jumps, which are mathematically described by this. And so this is the story. So you take the wave function, psi, and then at some random time, it happens, a jump occurs, which mathematically means that the wave function is multiplied by this jump operator, becomes this one, and then you have to normalize. So Lxi is a jump operator, which is defined here, it's just a Gaussian operator. So L is a the hat goes over here, is a Gaussian operator, is a function of the position operator, so it's a so it's a collapse in space. It's a collapse in space. I refers to the particle. If it happens for particle 1, particle 2, particle 3, x is the point in space around which the collapse. And these are also, that's the game. Then we will make some simple example to better understand what goes on. So this is a definition of a jump. Note, it is nonlinear. So the operator L is a linear operator. But the collapse is this one. You multiply psi by L, but you want to normalize to 1. And the combination of the two things make the process nonlinear. It's a collapse of the wave function. You mean the base? In which sense you mean the basis? The motivation is the one I gave you before. You want to build a model with a unified dynamics, and this dynamics describes the quantum property of matter as we know it, and it contains the von Neumann collapse of the wave function during measurements, and describes the classical property of macroscopic systems. So everything is contained in the dynamics instead of standard quantum mechanics, where you have the unitary evolution, and then you assume that at random times the unitary evolution stops and you have the collapse. I don't know if that answers. So that's the motivation. Otherwise, it's an assumption. Now, if you ask Adler, Stephen Adler in Princeton, he would tell you that these dynamics, so together with the Schrödinger dynamics, is an effective description of an underlying pre-quantum theory, which he calls matrix dynamics. Different names. But in general, he would tell you that this is a phenomenological description of an underlying, fundamentally nonlinear process. Fundamentally nonlinear. Stochasticity at the fundamental level is not there. Stochasticity comes at the effective level because we do statistical mechanics of the underlying theory. So the stochasticity comes from the effectiveness of the model. Nonlinearity is a fundamental property of the underlying theory. Yes?
In any time, I mean, not only when you measure.
That's the fundamental requirement. They happen any time. Now I will give you numbers and things will come.
And this psi 2, I mean, if I am not understood wrong, this psi itself is a multi-component psi, so which has multi-particle indexes.
Yes.
So it jumps to one of the psi x particle indices.
Say it again, the last part.
So psi is psi you can written as psi x1, psi x2.
Yeah. It is a, yes, you're right. It's psi of x1, x2, xn. It's a multi-particle wave function.
Yeah, I mean, in simplest case, they're just product.
Not whatever, whichever state.
Yeah, I mean, in general, they're anything. So from that, it will collapse to one of the particle state.
No, not necessarily. The collapse is described by this Gaussian. The final effect depends on the form of the wave function.
Okay, so psi xi, what does this stand for?
Psi xi means exactly nothing more than this.
Oh, it's not correspond to ith particle or something. Okay.
No, okay. It means only this. It means you have to remember that a collapse occurred with reference to particle I, and I'm saying with reference to particle I, I'm not saying that it has collapsed, but that depends on where we are. So I just want to keep track that something occurred to particle I around position x of space. And it means at the moment nothing more than this. Because the final state depends also on the initial state. Is the collapse state. What that means will become clear next. next hour. Yes? Spontaneously. The game is that nature is like that. I will tell you next hour. I will. And if I don't, remind me. But I want first to say a few things, then to come to answer your question. Okay, let me just finish the dynamics, and then we stop, and then we continue. So, in principle, so really don't think that this happens only during the measurement process. Of course, there will be a building up mechanism during measurement. But it is something that happens all the time, everywhere, for an isolated electron, for in a matter, for the wave function of the universe, whichever physical situation. You should consider now as the fundamental dynamics of nature. Nature goes like this, not just in special situations. Always goes like this. So the collapses are, as we said, random in time. They are. So the assumption, which is just a simplicity assumption, is that these collapses are, the important assumption is that they are randomly distributed in time. The simplifying assumption is that they are distributed according to a Poissonian distribution. Controlled, which is not, because it's rather natural, and also because it's simple. It's controlled only by one parameter, the rate of events. And this is the second parameter of the model. So there are two parameters. These are C, which has the dimensions of a length, and lambda, which has the dimension of a rate inverse time. These are two new parameters. So this model is a phenomenological model, so these are phenomenological parameters. But if you think of it as the new fundamental law of nature, then these are two new constants, like h bar. But the jumps are random in space. We don't know where they occur around point x, but we don't know which point. And the probability density for the particle I to experience a jump around position x is equal to, I'm done. 2 minutes and done. It's equal to psi, this one, psi I x square norm. That's not normalized. This is the normalized state. That is not normalized. So it's not 1, which is different from 1 in general. You can prove, so if you wish, it's another exercise for you, that the probability integrated over space is equal to 1. Otherwise, we cannot call it a probability density. And then it's a little exercise, check that that is true. Okay, so this is how they are distributed in time, Poissonian, and how they are distributed in space. Last piece. In between collapses, you have the Schrödinger evolution. Yes. We will see it later that when we want to build a statistical operator, we will show that this is the only possible choice to kill nonlinearity. Yeah, well, it's the norm. You see, it's the norm preserving term. But I want to do that. I want to connect that later, just because I don't have time now. So I mentioned to let me finish. As I was mentioning to TP to connect to what I said before, but I will explain it later. The process is nonlinear. It is also stochastic. As I said before, you cannot take stochasticity the way you want. You have to take a specific stochasticity in order to avoid superluminal signal. And that's hidden here. I will show it to you later. That is because I made this choice, which is basically the Born rule, basically. I can counteract nonlinearity and arrive at a linear evolution for the density. So I'm playing the game that I did before. Yes.
There is a Schrodinger equation, and I mean, the collapse itself is spontaneous. Instantaneous. At what space-time point collapse will happen, that we choose by the statistics, but collapse is instantaneous.
They are spontaneous.
Instantaneous.
Say it?
The collapse process is instantaneous. there is no time evolution.
And this model is instantaneous. Then there are refined models. I will say again. I will comment that next.
So the probability distribution for this space and time is to pick the random sample where the collapse happens.
The collapse is instantaneous in time. So at this time, nature decides to make a collapse for particle I, with which probability you take the wave function at that time. You take the wave function at that time when the collapse occurs. You multiply it by this operator, you compute the square norm, and that's the probability. That's the game. I don't know if it's clear.
Yeah.
But in this model, they are instantaneous in space. So just to finish, and then I'm done, we can go for lunch. You should see that for any physical system, in any physical situation, whatever it is, not measurement, forget about measurement. It's Schrodinger, and then randomly in space and time, and instantaneously jumps. This is the GRW, and then last comment, and I promise. This is the GRW model, end of the story. States, dynamics, nothing else. In quantum mechanics, you have states, dynamics, observable as operators, Born rule, collapse. All these things follow from here. Here, I haven't talked about operators and observables. I haven't talked about measurements. There are just states and dynamics. Everything else follows. So to come with the question to one of you, I will tell you next hour. Okay, if there are no further questions, we can stop here. Oh, tell me.
They are, they are the same constant for every system.
Universal constants.
Okay.
Phenomenological, but universal. You don't pick the different numbers for different situations. Thank you.